Hello and welcome to this short video that introduces the Smart Collectives Orchestration Manager. The Smart Collective Toolkit contains many different components that can be used to build smart society applications. In this video, we will describe the Orchestration Manager that is responsible for social orchestration in the system and can be linked with several of the other components. What is social orchestration? Social orchestration is the process of organizing the activities of various peers when they collaborate on a smart collectives application. It involves several stages, starting with the discovery of different peers and, importantly, the composition of possible tasks that will satisfy the task requests of these peers. If one doesn't want to show all possible tasks to peers, then a recommendation element is required that will cut down the set of possible solutions to those that seem most relevant to peers and that they can choose from. For certain orchestration patterns, the peers will have to negotiate their participation in a particular task and agree on joining a specific task as a group. Execution follows this negotiation, and this is when the actual task is executed in the physical world in cooperation with an online system that will track the status of this execution. And finally, the peers can provide feedback to the system that will aid future orchestrations, for example, by learning more about the peers' preferences and composing more relevant tasks in the future. If you consider this from an interaction-driven perspective, then the different tasks that are required to complete an orchestration cycle can be viewed as different stages in a protocol that runs between peers and the orchestrator, so a server that runs the Orchestration Manager component. For peer discovery, the peers would advertise their capabilities, and they would also issue task requests that tell the system what kind of things and activities they are interested in. Task composition would then compute possible solutions and notify peers whether solutions are available, so that they can then be allocated to these tasks either based on a negotiation process or simply automatically by joining a certain task. We place great emphasis on giving peers the autonomy to choose which tasks they want to participate in, so we don't want to simply allocate them to activities. If agreement is reached, then we can move on to the task execution stage, which involves peers sending updates to the platform to track execution status. Finally, the peers from the point onwards where a task starts can provide feedback on this task and its participants. In the Orchestration Manager, these kinds of interactions are implemented in a completely data-driven way. So each of the different messages you have seen in the previous interaction protocol is mapped to an online resource, a document that peers can read from and write to. Of course, this is subject to access control and authentication, and the RESTful APIs that are used for the system also make sure that the different resources are linked to each other, that are related with each other through the orchestration lifecycle. For example, as you can see in this diagram, certain requests are linked to a task that is returned and composed by the engine if this task satisfies these requests. It's the same for negotiation. For example, if you look at the agree box, their agreement, of course, refers to specific tasks, and the agreement of several participants is required to actually make this task be executable. The Orchestration Manager uses a completely asynchronous event-based workflow execution system. So basically you have a workflow executor which fetches different individual small activities, also called jobs, that have to be executed on the platform to enact certain workflows. So you have different orchestration queues for different types of jobs, for example, authentication, access control, document validation, and so on. And the workflow executor is responsible for creating the appropriate work sequences of jobs for different things the orchestration manager needs to do. And then we have a job scheduler that fetches these jobs from different orchestration queues based on specified priorities they have to ensure that the orchestration manager responds fast and prioritizes those tasks that require more computational effort. To give you an example of such a workflow, we could have a sequence that is invoked during negotiation on a task and which involves several steps: authentication, access control, document validation to check what data the peers have sent to the server, and then, for example, applying a negotiation step. Let's say that a particular peer has just agreed to join a task. So enacting this on the platform requires several steps. The peer has to authenticate. We have to check whether she is actually allowed to write to this particular document and whether the data she sends is valid. And then finally, if we then realize that she has agreed, then we will also record provenance for this step to track what has happened in the system in the past, which is important for accountability and transparency. So the example you can see here on the right-hand side is exactly just the authentication job generated during this negotiation step that has emanated from a call to the RESTful API of the Orchestration Manager. The Orchestration Manager also allows for linking in delegated services. I've already mentioned provenance, but also, of course, there are other components in the Smart Collectives Toolkit, for example, the Peer Manager, that is used to get information about peer profiles, and it also provides authentication. We also have the Reputation Manager for obtaining reputation scores for peers. These will be important to select which people to match with each other and what tasks to generate. Incentives Manager is responsible for generating incentive interventions, prompting peers to act in certain ways and to provide them incentives. And the Task Execution Manager, which serves to record status updates during execution of a task. Orchestration requires the use of different so-called orchestration patterns. So the actual interaction workflow that specifies how users will engage with the system and what is required for activities to be orchestrated between them. In the model I have shown before in the video, what we have used is what's called continuous orchestration. In continuous orchestration, the users post task requests. Task composition produces tasks based on these task requests by creating matches that reflect possible collaborations between different peers interested in doing different things. If negotiation leads to an agreement, then these tasks generate task records, and from this point onward, the task can be executed. And also from this point onward, participants can provide task feedback. Continuous orchestration is a complex orchestration workflow that is only needed when you have group activities and people will work together on a shared task. There are simpler patterns, for example, the open-ended orchestration pattern we have implemented, and which doesn't require explicit negotiation and agreement. So here, a task is generated by an owner simply creating it. So, for example, this might be a question that you want to ask. And then participants can add or delete themselves from this task as they wish, although the developer can, of course, specify constraints. You might want to have a minimum number of answers to a question, or you may want to stop asking for questions once you've reached a certain number. As I said, overall agreement is not required here, and execution can start anytime after the task owner has created the task. So this is a simplified model that shows that you can have different variations of these workflows, and that the Orchestration Manager provides the flexibility to implement further ones apart from the two we have already provided. The focus of algorithmic processing in the Orchestration Manager is task composition. In continuous orchestration, we have to solve the combinatorial problem of allocating groups of users to share tasks. based on the task requests that these users have posted. Now, this may involve hard constraints, so really constraints that predicate what users' requests match each other, and that can be realized where certain tasks can be realized in principle, or soft constraints. So apart from just matching, we want to also consider things that reflect users' preferences. So even though something may be possible, it may not be something that the user might be actually interested in. Examples of task composition where this creation of group tasks is complex include things like ride sharing, scheduling meetings, recruiting groups of users to perform a certain citizen science task, and then there are simpler things like question answering, which I've already mentioned, crowdsourcing and so on, where you may not need to create groups by explicitly combining different peers' profiles and the profiles of their task requests based on complex combinatorial constraints. To illustrate why this is a complex task, consider a number of users, here shown on the left-hand side, and the number of possible tasks they could collaborate on. And of course, you have different users could work on different tasks, and several users could be involved in the same task. So basically, with the larger user populations here, you will have a huge amount of possible solutions. To add some intelligence to the system and enable the system to cut down the number of possible solutions that are presented to users, which after all would be too high for users to process, we also provide a component that is called the optimizer. The optimizer is an optional component that seeks to enable adaptive orchestration. So by adaptive orchestration, we mean that you may want to learn from past data what the preferences of the users are, and you may have derived models of the utility that certain tasks have for the users and for the system. Now, of course, there is a balance to strike here, because we may have system-level objectives, and then we want to also satisfy the user's objectives at the same time. So there might be conflicts and tensions between these objectives, and we need to somehow align them if we want to really account for diversity in the system. So our optimizer involves a complex optimization procedure, which, if you have specified preferences for the users and the system, will generate a set of optimal tasks that comply with several criteria. On the one hand, they maximize global system utility, which is of course application dependent. For example, you may want to maximize the occupancy of cars in a ride-sharing application. But it also aims to maximize fairness. Here, this is implemented as minimizing the difference between the individual utilities of the peers participating in tasks in a global task allocation among a user population. Finally, the optimizer also involves calculating incentives that will nudge users to behave in a certain way. So while we don't restrict users' autonomy, and any user may engage in any task they like, we generate a taxation mechanism which introduces very small disincentives for those tasks that would not be globally beneficial. So overall, this optimizer can be used as an alternative to the default, which is generating all possible tasks that come out of the matching procedure during task composition. So instead of generating all of them, here we would generate certain limited numbers of recommended tasks that the users can choose from. In terms of system requirements, the Orchestration Manager is based on Node.js and MongoDB for the backend system, so for the orchestration workflow and management system and the backend database, and runs as a server-side application written in JavaScript. If you want to use the optimizer, you will have to obtain a license for Cplex, which is a third-party software and not available in an open source or free version. The components you can download on our website contain the core orchestration system, which allows the developer to configure the task types used by the application you want to develop. These task types, so specifying what the attributes are and how these can be matched, need to be specified by the developer at design time before generating the database of the system. And then, of course, based on the application, the composition method may have to be overwritten to suit the needs of the application. So you will have to specify what constitutes a viable task given the different task requests posted by the users. We provide the two patterns of continuous and open orchestration. As I've said above, the basic difference here is whether you want to have explicit agreement by the peers participating in the task or not. And we also provide the optional optimizer component I've just mentioned. This can be plugged in to produce task recommendations, but it doesn't have to be used. We include simple demo examples of the two different types of orchestration workflows and installation instructions that will get you started and help you build your first orchestration manager system easily on your own server. We hope you will enjoy working with the Orchestration Manager components as part of the Smart Collectives Toolkit, and thank you for watching this video.